All right, radioactive decay. If we talk about rates, remembering back to kinetics, there is a defined term called a half-life, and that's the time required for half of any given quantity to decay. So, for example, if we look at strontium, it has a half-life of 28.8 years. So, at the start of when we look at strontium-90 as a sample, say we have 10 grams. At the end of one half-life, 5 grams will be remaining. At the end of two half-lives, 2.5 grams will be remaining, and at the end of three, 1.25. So you can see how each successive half-life, I have half of it remaining. Remember, this is not a linear function. Okay? It is not a linear function. Go ahead and graph that if you don't believe me. Otherwise, just take my word for it. The other thing to remember is half-life is not affected by temperature or pressure or anything else. Okay? Just radioactive decay happens. So, the half-life of cobalt-60 is 5.3 years. How much of a 1.00 milligram sample is left after 15.9 years? Well, first thing to figure out is how many half-lives is this? Well, 15.9 years divided by 5.3 years in one half life is 3 half lives. So, if I start off with 1 milligram sample, after one half-life I will have this much remaining, half a milligram. I think I added an extra 0. After the second, and then after the third half again. So this will be 1, 2, 3 half-lives. I'll have 0.125 milligrams remaining. And that's really the most, I think, straightforward way to calculate those types of problems. So one thing that we slid over in the previous screencast is the uses for radioactive material. Cobalt-60 is used to sterilize hospital equipment using gamma radiation. It is used in cancer treatments, radiotherapy. Iodine-131 is used as a medical tracer. It emits both beta and gamma radiation, and they can track that. Diagnose and treat thyroid cancer. It has a short half-life. You also have iodine-125 used for prostate cancer. It has an 80-day half-life. It is a beta emitter. If you want more than just this quick overview, there is a little bit more detail in your book. There's also mineral. You can compare potassium-40 to argon-40, the amount of uranium-238 to lead-206 to determine how old a particular mineral might be. You also have what is called carbon dating. The interesting thing about carbon-14 is that in a living organism, because of the CO2 photosynthesis process, the carbon that it takes in from the environment, the ratio of C14 to C12 is consistent until the organism dies. And then when that dies, it no longer is equal to that carbon 14-12 ratio that you find in the environment. That carbon 14 starts to decay. And it's that presence and the decay of C14 that allows us to carbon date materials. And this gives you some idea. So if, say, if this is the day that the organism dies, you will have the same C14 that you have as in the environment. So this is really equal to the carbon 14 in the environment. And then when 50% is remaining, it's 1 half-life. And you would know that the animal or plant or the organism is 5,730 years old. So that's really how they date it, by looking at the carbon 14 content.